Okay.
The only one?
Yep. All right. So ready to start? All right. So.
I just miss you so much. That's illegal.
Where is he?
All right. Okay. So we're still looking at conic sections. So what are the types that we've looked at thus far?
Parabola.
Maddie.
I forgot what I was saying.
Guys, oh, hey. Maddie.
Parabolas and circles.
We've looked at parabolas. We looked at circles. Okay. So if I have this, what does this look like?
Circle.
Ah, it
From the top.
looks like a circle.
It's an ellipse.
Oh.
Really? We got our.
I was right.
Yeah.
No.
Yep. So
No.
I really can't.
I thought it spins on its own. That's such a cool design thing.
It is, but sometimes I want to look at it head on, so I have to stop it.
Oh, that sucks.
I know. But it's really cool, right? So we have this cone. So far we've looked at parabolas. Remember, if this whole section, this whole unit is about slicing up this cone. So if I take this plane and I cut it through here, what do I get?
Parabola.
There's how I get that parabola,
It's an ellipse.
right? So it's not quite an ellipse,
I want
right?
it to be an
Because
ellipse.
what do you notice about this slope here?
It's too like
It's linear.
What's that? Yeah, so it's always going to be inside the cone. This cone is always going to grow out and out and out. So if we look here, this part will always grow out, whereas this parabola will always stay inside. So we're going to see the ellipse is actually fully enclosed, which this isn't.
it just
Looks
slams
like
in the
Scooby-Doo.
Now if we take this plane and we have it exactly parallel with the base of the cone,
Circle.
that's when we get our dear old friend, the circle. That's what we've looked at before, right? So where we're looking today is this. So we can see it's slanted just like that plane with the parabola. But here, how would we describe the slope? So, what's that?
It's an ellipse. Oh wait, no.
It's
Right, and how would I describe the
The
slope?
slope is less severe, and therefore it crosses 2 points.
Less severe?
It's more horizontal.
Yeah, so it's a lesser slope, right? The slope is not as great. It's
not
more,
as severe.
right? This plane is fully enclosed within the cone itself. So that's why from the top down we get the circle view, right? So that's what we're going to be looking on today. We're going to be looking at ellipses. And ellipses, they're like circles. They're just a wee bit more complicated, but
Like
nothing we
ovals.
can't handle, okay? And then this is, of course, what we're getting to later.
Wow, that's so dope.
Hyperbola.
Yep.
Bobby
It's
dog.
also do- Bobby dog.
It's vertices or Bobby dog.
Same team. All right, so we're abandoning that for right now.
Aww, look at your little background. Mr. Cahill.
And
Yes, that's
we see the otter with the rock.
That's my red pen.
It's not in water.
Theo.
Stop playing invisible
Scott?
basketball.
Hey, playing.
I don't know what's going on. I'm scared right now.
All right, so there's homework that we did. All right, so again, here are the cones with their cross sections. You may remember this picture from Zmoodle. And now we're dealing with this ellipse. So anybody ever play with spirograph or strings or stuff when you were doing artwork as a kindergartner or whatever?
No.
Yeah, I guess like spinner.
Definitely not.
Yeah, exactly.
Oh, I remember that.
So here's what actually happens with an ellipse. Notice it's this chain, and it's got these. Good, the two foci, right? So, one focus, two foci. So, what actually happens is we actually are going to have any point on this have a special relationship with the foci. So, see how I have this wire here? What can you always say about the distance of this wire no matter how I twirl it?
It's the same.
It's constant distance, right? Constant total distance. So imagine now, I have 2 points here where this is connected, and I take a marker and I drag it around like such, right? What do you notice about the distance of these individual lines?
It's equal.
Well, what's equal? Because look here. Look at
The
that.
radius of
They, the distance is the same.
Well,
The distance,
I don't know. That's
if the
wrong.
individual ones are different, but like the equal is the
How are they different? So like if I look here at this one on the left of this point, one on the look on the right, which one's bigger? The one on the right's bigger, correct? But now as I tilt this over to the left, what happened to the one on the left?
one on the left is bigger.
The one on the left got bigger when the one on the right got smaller. But what about the total distance?
It's the same.
Stayed the same. So if I keep going around like this,
Wow.
looks like it has hair.
Boo.
What is that?
An ellipse.
Bad drawing
That is an ellipse. That is how we get the ellipse. So here's what's happening. And yeah, now I got red all over it. So we have our two foci. And we're going to have an infinite amount of points all along the perimeter there. The distance from that point to one focus and the other focus is going to vary. However, the sum of those two distances, d1 plus d2, is going to remain the same. It's going to be a constant. So just how I drew it with this piece of wire going around and making the ellipse, that's how we formed this. So think back to the parabola. What was special about the directrix and the focus with the parabola?
They dictated a spot on the parabola.
How?
They were two equidistant lines from the directrix and the other one. Focus.
Good. So each point on that parabola was going to be the same distance away from the directrix and the focus. So just like we could have made a string drawing there with the parabola, here we're getting the same thing done with this ellipse.
Wait, so D1 and D2, they aren't the same measurements.
They're not the same,
But them together is always going to be.
the same.
the
So let's take a look-see, all right? So perfectly drawn ellipse. I know, I'm pretty good. And we have our two foci.
Piggy nose.
What's the name of the guy in Big Hero 6? Yeah.
All right, so we're gonna have a point. Let's say this point is here, right? So I'm going to connect this point with each focus. A little bit.
Are they?
Wait,
the
if they're
focus-
always the same, then what number are they always
We'll go. Don't worry.
are
Don't worry.
the foci
Foci. Yeah.
different? Like, I mean, the same length from the outside. Like, so there's the end of the circle and then the foci. Is that the same?
So are you saying like, is this distance the same as
Yeah.
that distance?
Yeah.
Yeah, we're going to actually break down the formula in just a second. I just want to highlight this relationship here. Okay. So say this distance is 2 and this distance is 5. What's their sum? 7. So now let's take a point here. And so I connect that point with each focus. And let's say that this point here is, this distance is 4. So what must
3.
the other line be?
3.
Why?
Because 5 plus 2 equals 7, and they're about the same distance.
thought it'd be like-
Good. So each point, right, and I just have 2 there, but there are an infinite amount there. Each point, the distance from that point to each focus is going to be a constant sum all the way around. So here's 2 and 5. It's 4 and 3. It could also be 1 and 6. 6 and 1. Clayton?
And it's actually stupid. Don't worry about it.
You sure?
Yeah.
Okay.
Wait a minute.
Go ahead.
I'm sorry.
How do you know that's 4?
So I gave you 1, right? Ah. So I said 2 and 5, right? Let's just say that this is 4.
Okay.
We used the distance formula. We found the exact points.
Oh, so
We know it's 4.
You don't need to use the distance formula for the other one.
Right,
you know
because
it's-
that we know that's 3, right?
Okay. Okay.
Cool.
So then, could you do another point off of like one of the other focuses?
Yes, I mean I can do any infinite amount of combinations here and get their respective distances. So if that's 1, what's this distance?
6.
Very good, because they always add up to 7. All right. All right. So, where's the center of our ellipse going to be?
The midpoint
In
between those
the
2
two
points.
the foci.
So yes.
That
Yes.
was what I was going to ask that I thought was stupid.
No, that's good. That's actually a little bit more detailed than what I was going to ask.
Okay.
Like in this section, where's the center of the ellipse?
In the middle.
In the middle. Wise. So wise.
Are you simpler?
That was just
Okay, where was the center of the circle we looked at in last section?
Origin.
The origin. So where's the center of this ellipse going to be?
Origin.
Origin. Remember, in this unit, we're going to go through. We're going to look at each conic with the center and vertex, etc., at the origin. Then the last section, we're going to ship them all around. So today, with our ellipses, where are they going to be centered?
0, 0.
0, 0 at the origin. So if I have an ellipse that's centered at the origin, how many different possible ways could it go?
Lots. Infinite.
2. How could it go?
Vertically or horizontally.
Right? So it could be
Oh, yeah.
like that, right? Or it could be like that.
Does centered at the origin mean that it's inside the cone?
This is the center.
So no matter what way it goes, the center is up.
This section is going to be entirely in the cone. Yes.
Isn't it like if A is bigger than it goes?
Are you gonna have me?
Isn't that one and then if A is smaller?
You're right, but you're looking at me. So hold on to that thought. Hold on to that thought for just a second, all right? So here's all the fun little graphs. I stole these right from your textbook, so that it's going to be a little bit easier for us to look at these, right? So, just as Sophie pointed out, we have 2 ways that these ellipses could go. We could have it sort of lying down flat on its side or standing straight up. You're going to have 2 axes here. And don't say X and Y axis. I just drew them, right? The red and the blue. How would you describe them? What?
The length and the width.
Length and the width. That's a good way to say it. The red one, we could call that the length, is always what?
Longer.
Yeah, see how this red axis is always longer? The blue one is always shorter. What's at the end points of those red axes? What?
Vertices.
The vertices, right? And what's on the end point of those blue? The co-vertices. So a new little friend.
Get out.
Red one's longer, correct? So we're going to call that the major axis. You guys get that back there?
Yes.
What do we call it?
The major axis.
Yeah, the long axis is going to be the major axis, and the shorter axis is going to be
Minor.
perfect.
So is A the longer?
Yes, still on there, but hold on to that thought, okay? So we have these 2 axes, right? So if we think about, the 4 corners of the Earth, sounds pretty stupid, right? The sphere, how can there be 4 corners? Well, here we're going to talk about the 4 corners of this ellipse. We have 2 co-vertices and 2 vertices. The vertices are the endpoints of the major axis, and the co-vertices are the endpoints of the minor axis. Yep.
Okay.
Okay.
So you said that there are 4 corners of an ellipse. Does that mean, that an ellipse is a quadratic?
You're so stupid.
No. So I was saying the 4 corners just to make like a point that there are these 4 points on the outside. Typically, we don't call them corners. And yeah.
certainly don't call them graphs.
Yeah.
I'm gonna find a way to prove that.
In all fairness, everybody's kind of laughing at you and all this stuff. This is probably more closely related to a quadratic than other people might believe. Remember, because these are all conics. Another type of conic is parabola. So you're thinking,
But not.
right? So we know, we can see down here that there are two formulas. I'm going to write these so they're a little bit bigger. X squared over a squared plus y squared over b squared is equal to 1. And we have x squared over b squared plus y squared over a squared is also equal to 1. What changes with those two formulas? So, Sarah?
A and B switch.
The a and the b switch spots. Why might this happen? Maddie?
Because when the A is under the X, it means it goes horizontally.
Good. What does that a represent with all these
The
points?
major axis.
The a represents points that are on the major axis. And what points are on the major axis? The other points.
Oh, the vertex.
Right? So if you, this is kind of a little bit blurry on the big screen, but the vertices are going to be a comma 0, negative a comma 0. That a value represents the vertices. Over here, when we have this vertical major axis, it's 0 comma negative a and 0 comma a. So it's still that a value. That is the major axis. So if we look with the horizontal major axis, this one on the left here, we see that the a squared, that a value, is paired with the x squared. Because this major axis is on which axis of the plane? Yeah, it's on the x-axis. Whereas over here, that a value, that major axis, is on which axis? It's on the y-axis, so that's why the a switches. And then the b value represents
Maya.
you don't have to whisper it, right? What? I still don't know why you're whispering.
The covertex.
Okay, all right. Yes,
Better than the alternative.
the b represents harsh. The b value represents the co-vertices. Again, so we look at this graph on the right, this minor axis with endpoints at the co-vertices is on the x-axis. So that's how we get there. Maddie?
So like when you're solving for A, so like when you divide like everything by like, so to make that one, you divide it. So whatever one's bigger is going to be A, like on bottom.
Why would the a value always be larger?
Because the major axis is larger.
Right, because that a value represents the distance from the center out to the vertex, either one. So if the b value is larger, that means that the minor axis is larger than the major axis, which by definition can't be the case. So you're right, the a squared value is always going to be larger. That's going to help us later when we actually find out how to match these equations. All right. One other quick note that we have there, we mentioned the vertices, co-vertices, the center. We totally forgot to talk about our foci, correct? We're going to have one focus on each side, right? So the foci are located, how would you describe their location?
Midpoint of the radian.
I mean, there in that picture, it looks like the midpoint.
Is it
It's-
always on the x-axis?
Well, over here, they're up there.
It's always on the major axis.
It's always on the major axis, right?
Major axis.
The foci are always on the major axis. Do you have something to add?
They're equidistant from the origin.
Yeah, so just like your vertices and your co-vertices, they're all equidistant from the center, right? Your foci are located at 0, negative c, 0, c, c, 0, c, negative, or negative c, 0. They're all sort of opposites. So if the focus is represented by c, how can I find that value for c?
Can you repeat the question?
if the C is representative of the vertex, how do I find the value of C?
C
Oh, it's opposite of Pythagoras.
Doesn't C have 2 equal 1? C squared equals A squared minus B squared.
C squared is equal to A squared minus B squared.
Son.
Oh, I don't know how you got that. Right?
In my brain.
Right. So look, there is some relationships we can look at. We're running a little bit low on time, so we're not going to go into that. But look, to find the focus, the foci, the C value, all you need to do is A squared minus B squared, right? And here's a nice little summary. This is in your packet. It's in your textbook. It's going to be up on the website. It's going to be everywhere. It's a nice little summary table. So as you go through these problems in your homework, reference this, because again, the first time you look at these problems, try a graph. It's not going to go over perfectly, so don't be intimidated. But if you're looking at this, it might help you. All right, so let's actually look at an example. So they give us this equation: 4x squared plus 25y squared equals 100. We're going to identify the vertices, co-vertices, and foci of the ellipse. Well, where's the center going to be? 0, 0, which is wonderful. So we're already like halfway there, pretty much. Now, this looks different from the other equations we've seen before. Sarah?
You have to divide both sides by 100 because it's equal to 1. And before the 25 will cancel out with the x squared y squared.
Yeah. Right? So if we look back, these are the two equations of our ellipses, right? In both cases, they equal 1. Here, yeah, it has different coefficients for the variables, but the big thing is it doesn't equal 1. So what we do, is we divide everything by 100, each term. So what's 4 over 100?
1/25.
1 over 25. So we're going to have x squared over 25. 25 over 100 is?
1 over 4.
So we're going to have y squared over 4. And 100 divided by 100 is?
1.
So that looks like our ellipse.
So,
Right?
so it would be horizontal.
Why would it be a horizontal?
Because, so A is going to be 5 for below x squared.
How is a going to be 5? Why wouldn't a be 2?
For x squared?
Well, how do you know that? So you're saying that this 25 is equal to a squared, correct?
Yeah.
Well, we looked at two formulas. How do you know that the a squared is 25?
It's 25 bigger than 4.
Right? And the 25 represents, like the a value represents what?
The bigger
Which
major
x?
axis.
Yeah, it's the major axis, so it's going to be larger. So basically here, you know 25 and 4, one of them is going to be a squared, one of them is going to be b squared. So which is which? The larger one is going to be situated on the major axis. So that means that a squared is 25, b squared is equal to 4. So what does a equal?
5.
And what does b equal? Questions about that? Mm-hmm.
Wait, so then the vertices are. How many points are there then? 4.
So let's take a look, right? So this is going to be, my major axis is going to be on which axis?
Horizontal.
Let me call the horizontal axis the...
X.
Good. It's the x-axis, right? The major axis, the larger value, is going to be situated on the x-axis. So a is 5, right? We can think about the points it represents or realize that's a distance. So we go 5 in either direction. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And what do these 2 points represent? These are my vertices. Now B represents co-vertices. So distance from the center, right? So which axis are they going to be on? Right? The D value, my minor axis, is located on my y-axis. So I go up 2, I go down 2. Now I need 2 special points to really make this ellipse perfect.
Foci.
So that letter that represents my foci is C. So in order to find C, what do I do? So I get C squared to be 25 minus 4. So C squared is equal to 21. So C is equal to the square root of 21, which is about,
4.5-ish.
yeah, so it's going to be between 4 and 5. It's actually closer to 4.6. So we're just going to eyeball it here. So it's like 4.6, 4.6, focus, focus. Connect the dots, everybody's favorite. And there we go.
Cute.
Right? Matt, you have a question?
It's like an eyeball.
Yeah.
I was actually thinking like, hey, Arnold's head. You know?
Yeah,
So wait, I don't know. The focus
Rough.
is on the. It's always on the major axis.
Your 2 foci are always, always, always going to be on the major axis. Right? They're chilling with the vertices, while the co-vertices, they're just sort of off alone.
So okay. So it's gonna like go. It's gonna touch like the focus and the co-vertices. It's not gonna touch the vertices.
Correct.
Wait. What
Okay.
was the question? My question? Yeah. That it's gonna touch the co-vertices and not the.
You have a question you want to add there, bro? Okay, so one of the important things we're going to have to do is get some practice. So we got some practice problems to do.